Good morning. Welcome to this Grow Your Knowledge webinar, which presents the results of a 3-year collaborative study on how the near zero energy buildings standard may be achieved for UK residential and commercial buildings now and in the future under changing climate. My name is Anastasia Melona and I'm head of research at CIPSI. The outputs of this study are also published as a research insight, a CIPSI publication. You can find that online and download it for free through the Knowledge portal, but also it will be in the email that you will receive tomorrow, along with the link to the slides and the audio of the webinar. The research that is presented today and in the publication has been conducted by Radoa Salem. She's a PhD candidate at the University of West London, and she's been working under the supervision of Professor Ali Bahadori Jahromi. So we have those two speakers today. Professor Ali Bahadori Jahromi is a professor of civil engineering, fellow of the Institution of Civil Engineer, and head of the Building Performance and Climate Change Research Group at University of West London. His research group has produced several research outputs, a number of PhD graduates, and successful collaboration with partners from the software, hotel, industry, and professional bodies like CIPSI. Given the complexity of energy and sustainable design, Professor Bahadori Jahromi internationally adopts interdisciplinary approach to his research work. His research draws on insights of architectural studies, civil and mechanical engineering. On his current research interest is the application of computational modeling and simulation for sustainable design. Our second speaker is Radoa Salem. Radoa's research interests lie in the environmental performance of buildings with a focus on the energy analysis of buildings, building simulation, and sustainable design. After completing her civil engineering degree, she obtained a scholarship to complete her PhD research in collaboration with CIPSI and Hilton Hotels at the University of West London. Her PhD examined how UK residential commercial buildings can be retrofitted to achieve the nearly zero energy building standard. She is particularly interested in investigating ways to achieve sustainable building design with cost benefits to the relevant stakeholders and how those buildings can maintain their performance long-term under future changes in the climate. So as I mentioned before, the slides and the audio will become available to all attendees tomorrow. An email will be sent along with a link to the accompanied publication. Regarding today's webinar, we are going to listen to the two presenters, and if you have any questions, please add them to the question function on your dashboard, and I will go through as many as possible after the presenters have finished their presentation. Thank you all very much for attending, and I will let Ali start his presentation. Ali, over to you. Thank you.
Good morning and welcome to the webinar for design and evaluation of nearly zero energy buildings. This webinar, as my colleague mentioned, summarized the result of a 3 years collaborative study on how the NZEB standard may be achieved for UK residential and commercial buildings. 4 UK case studies will be discussed, including a typical pre-1990 detached dwelling, a retirement village, a historical hotel, and a typical purpose-built hotel. The outline, we start, what is the definition of the NZEB? What is the NZEB concept? Very briefly, I will explain the methodology we adopted, and then we move to the case studies, and we finish the session with a conclusion and question and answers. So what is the NZEB concept? The 2010 Energy Performance of Building Directive has set out a requirement for new and retrofitted commercial and residential buildings to be nearly zero energy buildings. This proposal was a result of previous and current statistics and research, which demonstrated that urgent action is needed to reduce building energy consumption and emissions. The Energy Performance of Buildings Directive had only provided a generic definition and no specifications. As a result, an open interpretation has been left for member states. The concept behind a near zero energy building means that it is a low energy demand building complemented by a renewable or microgeneration systems. The table we have here is showing a summary of the NZEB targets that have been aggregated based on research data. It also worth mentioning that the NZEB standard differs from other building energy efficiency methodology that have been proposed due to its focus on achieving the standard with cost benefit. Consequently, the NZEB standards provide improved environmental outcome while ensuring profitability. Here we have the general methodology we have used in 4 phases, starting with actual site data. This phase involves conducting a site visit to collect and produce AutoCAD plans, information for the actual building construction, system, and plant details. In addition, the actual monthly and annual energy consumption is collected for the latest year and the previous 2 years for comparison and validation. The reason we collected like a 3 years worth of the data for energy consumption to normalize the value in case we had a particular hot summer or cold winter. And then we use the result for the validation of the model. Then we use this data with task software to build a holistic baseline model. And then we incorporated the CIPSE weather data. We used the design summer year weather file for overheating analysis. And we used the test reference year for energy analysis and for compliance with UK building regulations. In final phase, we used the building life cycle cost software to carry out the global cost calculations. So coming to the first case study, the first case study investigated was a residential dwelling located in Bracknell, Berkshire. The dwelling is a typical pre-1990s building, and the building regulation it is built are well below today's standards, so making it more challenging to retrofit, as it typically requires more energy efficient measures, or as we refer to it later on, EMs, to be incorporated before the energy demand is lower. We used 10 different retrofit scenarios to investigate the life cycle cost analysis. We also used a sensitivity analysis. And finally, we have done a cost optimal solution. Per Energy Performance of Building Directive guidelines, or EPBD guidelines, individual energy efficient measures, or EEMs, were selected and then grouped into retrofit packages or sets, as we can see in a table. These sets are the retrofit scenario of dwelling, with one scenario being existing state of dwelling, which we refer to it here as a E0 or baseline. Area of focus to retrofit are categorized based as thermal insulation, heat, air ventilation and cooling, lighting, glazing, and renewable and micro generation systems. This table is just the result of the simulation for the various scenario in comparison to the NZEP target. And the baseline again is the E0 scenario. On a purely energy target basis, it seems that E10 is the best solution. Scenario E1 and E2 were specifically selected to provide an improvement from the baseline scenario, but not meet the NZEP target. The reason we have done that, because incorporation of such scenario provide an interesting comparison against the NZEP options. This is due to large difference in initial investment costs. Here we can see the summary of life cycle costs calculation. The different elements making up the life cycle costs for each scenario sorted into 3 categories as energy cost, maintenance and replacement, and miscellaneous costs, refer to any investment cost not related to energy efficient measures, basically. The comparison of the cost contribution of the different element of life cycle costs shows that for scenario E3 to E10, the capital investment costs are the most significant costs over the 30 years calculation period. In comparison to this, the most significant cost in a E0, which was the baseline, and E1 and E2, which was a slight improvement compared to the baseline, the main cost of this E0 to E2 will be the energy costs. It is unsurprising to see that baseline scenario has the highest annual energy cost in comparison to all other scenarios. The total life cycle cost of the different scenario is lower than the baseline scenario over the 30 years study period. This means that regardless of which scenario is selected for retrofitting, the selected scenario is in fact the cost effective. Or in other words, we can say not retrofitting the property is the most expensive option and least profitable over the 30 years calculation period. Then we consider effect of varying the weather file. As we know, the weather is changing, and we look at the 2020, 2050, and 2080. So the scenario were simulated and the future climate projection to see the effect of implementing NZEP retrofit under potentially different climatic conditions. The energy cost of the scenario were calculated based on the new energy consumption value generated under future weather projections. The future weather projection investigated are the high scenario for the 2020, 2050, and 2080 weather data. The figure shows a decline in net saving as future weather projections are simulated for the NZEP scenario. Meanwhile, for scenario E1 and E2, there is a slight increase in the net saving. This is because the projection showed a continuous increase in temperatures over a stipulated timeline, which led to increase in energy consumption. The high level of insulation and air tightness for the NZEP scenario meant that cooling demand increased significantly in comparison to scenario E1 and E2, which didn't include improvement to the building envelope and therefore not affected in the same way as the NZEP retrofit scenario. We also investigated the effect of the fuel cost. What will happen if the fuel price increase, and what will happen if the fuel price decrease over the future years. For all these 10 scenarios, again, that is investigated, as you can see from E1 to E10. So looking the figure, an increase in the fuel price by 5% has meant that all the NZEP retrofit options become more cost effective. On the other hand, increasing the energy price meant that scenario E1 and E2, which are heavily affected by the fuel price, as opposed to the NZEP option, had a significant increase in their energy life cycle costs. Then we look at the decrease of the fuel price. A decrease in fuel price by 2.5% and more will cause the NZEP scenario to become uneconomical. This is because the life cycle cost of the E0 scenario or baseline decreased significantly. I'm aware at the moment, because of the current situation, the price of the fuel is dropping, but this is unlikely that is sustainable scenario, and probably within the 6 months or 7 months that will pass. So our assumption is very unlikely that fuel price will be experiencing any significant reduction compared to the current price. Also, in contrast, an increase of 2.5% or more significantly decreased the economic viability of scenario E1 and E2, which we said is slightly better than the base case scenario, but not the NZEP. A 5% increase or more means that those two scenarios will no longer be generating any substantial net saving. Then we look at the cost optimal solution. From our cost optimal graph, we can see the cost optimal level for the retrofit of this dwelling is actually 75 kilowatt hour per square meter per year, somewhere around here. One of the simplest way to, so there is an issue here because the target of the near zero energy building is actually 44 kilowatt hour per square meter per year. So there is a gap between the current NZEP target and the established cost optimal level. So the simplest way to bridge this gap would be to improve the rate for the currently available incentive schemes and possibly introduce a new one like the one government introduced yesterday. So this sort of incentive could reduce the gap between the cost optimal and the actual NZEP target. In real life application, the cost optimal solution will largely depend on requirement of the investor. However, the same step of creating several retrofit scenarios and comparing them is key to reaching the NZEP standard with cost optimal level. We are moving now to second case study, which we look at the overheating. The second case study analyst is the retirement village in High Wycombe, and the overheating criteria utilized is the CIP-CTM 59 design methodology for the assessment of overheating risk in homes. So briefly, if we go through the case study summary, here we have the case study details, which is made of 7 blocks from A to H, and flats within the village have an average of 2 occupants per dwelling. Flat occupancy type is split into 70% residential occupancy and 30% nursing occupancy. The aim of this investigation was to assess how the case study building performs under current and future climatic conditions, as it currently is, and once it is retrofitted to the NZEB standards. The table we have here is showing a summary of selected energy efficient measures, or EEMs, that make up the NZEB retrofit scenario. Similar to the previous case study, we create a different scenario based on the energy efficient measures. We also look at the current literature. From the currently available literature, it could be predicted that the NZEBs and energy efficient building are more likely to experience overheating. Findings from the literature also suggest that incorporating of shading device, double glazing as opposed to triple glazing, and utilizing natural ventilation are currently some of the most effective ways to mitigate the risk of overheating. These measures were therefore incorporated as part of NZEB retrofit of this retirement village to see if it's possible to mitigate the overheating by considering these factors. So here this figure is showing the primary energy consumption, or PEC, for the building as it currently is, and once it has been retrofitted to the NZEB standard. We can see that the space heating primary energy consumption decreases for both the baseline scenario and even more for the NZEB retrofit, as future timeline scenarios are simulated. Although the total primary energy consumption for the NZEB scenario under the future weather projection remains lower than the baseline scenario, it can still be said that the NZEB scenario underperforms, because if you look at the figures for present NZEB and 2050 and 2080, you could see that gradually the energy consumption is actually increasing. Considering the typically high investment costs associated with the NZEB retrofit and increase in energy usage in the future, this would lead an increase in the occupants' fuel and energy costs. So generally, with energy efficient retrofit project, the main economic appeal is the reduction in energy costs, meaning that if this were to be reversed under hotter weather conditions, the overall financial benefit and economic viability of this option would be significantly lower. As we mentioned, also the reason for that, because the NZEB buildings are more airtight and it has a higher level of insulation. So in the future years, the increase of the energy is coming because energy has to be used for cooling the building. So we look at based on the CIPSE TM59, we look at the overheating criteria. Looking at this figure, we can see that the NZEB retrofit model completely failed to pass the criteria under the dry summer year 2020 50th percentile high emission scenario. Unfortunately, the typically recommended mitigation strategy means using the shading, using the natural ventilation, using double glazing instead of triple glazing, weren't sufficient to reduce the occurrence and severity of overheating throughout this particular building. Severe overheating is experienced under the 2050 and 2080 weather projection for the NZEB scenario in comparison to the baseline scenario. The kitchen and bedroom are more prone to experience severe overheating. Basically, temperature is exceeding 35 Celsius. So as one mitigating option, 100 kilowatt combined heat and power, and then combined cooling and heating and power system were simulated as part of the NZEB retrofit package to see whether they could potentially act as a solution for this overheating scenario. With the CHP system in place, the building continues to overheat in exactly the same way as it did, whilst the other measures were incorporated. However, when we incorporate the CCHP system was able to ensure that the building doesn't fail the overheating criteria under the current 2020, 2050, and 2080 weather database. Out of the mitigating strategy that have been checked throughout the incorporation of the CCHP system was the only alternative that meant the building passes the criteria. Moreover, the baseline building bedroom and kitchen failed to pass the TM59 overheating criteria, meaning the CCHP alternative was once again the only mitigating strategy that fully passed the overheating criteria. Looking at the primary energy consumption of the retirement village as built and post NZEB retrofit with CHP and CCHP, both the CHP and CCHP have reduced the primary energy consumption of the building, as we can see through the graph, and their current weather condition, but more importantly, they both maintain the primary energy consumption so that it meets the required NZEB standard and their future climatic projection. So this itself is an improvement from the previous set of results where the NZEB target was exceeded and their future projection. Despite the significant improvement that the CCHP system is provided, there are problems associated with the use of CCHP during the summer within cities such as London. This is primarily due to the extra firing of boiler and pumping heat into the air to cool the building, which adds to urban heat island effect. And because of that, we are not recommending that as a solution for every scenario. The types of mitigation strategy will vary depending on the type, location, heating and cooling demand of the building, and various other factors. So the result of this study don't undermine the importance of continuing to improve the energy efficiency of existing building, but it rather aims to highlight the approach undertaken should be considered. One more thing to highlight about this study, we didn't also consider user behavior and interaction as a possible mitigating strategy. This was due to vulnerable population demographic. Again, further research that collect and examine the user behavior on overheating should be undertaken to assess the significance of occupant behavior on overheating within the building. We are moving to the third case study, and I hand over to my colleague, Dr. Salem.
Hello, Radwa here. Just to get straight into it, the third case study that we looked at was Hilton Edinburgh Grosvenor. It is an older building. It was constructed in the 1860s and it has a listed buildings consent. So that just means it's of special heritage value or interest. And that just makes the retrofitting process a bit more challenging because it narrows down the sort of energy efficient measures that we could apply. It's spread over 2 separate buildings, as you can see in the figure there. The type of construction is historical stone walls. It has some AC systems in the public areas. Certain public areas have also been upgraded to have LED lighting. Originally, the type of glazing they had was single glazed sash windows, and that's been upgraded in certain areas to double glazed sash windows. And really what we wanted to see with this case study was just whether we can reach the NZEB standard for such an old building or not. Yeah, next slide, please. Thank you. So here we have our model validation for this case study, and this is just a comparison of our actual energy consumption relative to the modeled energy consumption. And as we can see, there is a 4.60% difference between those two. So this 4.60% is an overestimation of the actual energy consumption of the building. But with simulation models, the accuracy of the results is going to depend on factors such as the weather data, for example, and that should, really replicate the microclimate of the building's location, which is very challenging to achieve, and it will always lead to some variation. Also, for this particular building, we did some more research and found that buildings that are being constructed from stone walls across the literature, there seems to be evidence that they have a better thermal performance than obtained from computational models. And the reason for this is because whilst computational models tend to consider stone walls as monolithic, in reality, your proportion of stone, mortar and air gas is going to vary, and this in turn will obviously have an effect on the overall simulated energy consumption. Yeah, thank you. So here we have the summary of the possible energy efficient measures that we could implement on the building. And once again, the sort of main potential areas of retrofit were categorized into insulation, glazing, lighting, HVAC, domestic hot water measures, and some microgeneration systems were trialed as well. So all of these were initially implemented individually on the building, and where applicable, various sizes have also been trialed. For example, if you can see for sheep's wool, it says 100 to 200 millimeters, which means we trialed 100, 120, and so on, as you will see in the next slide. So the first figure we're looking at here is showing us the energy consumption reduction contribution of each of those measures individually implemented on the case study building in comparison to our baseline energy consumption, which is the yellow dotted line, and how close this is to the NZEB target, which is the green dotted line. So generally, certain groups of measures are obviously offering a bigger contribution to the reduction of energy consumption in comparison to other groups. And for certain measures, such as the microgeneration systems, the energy consumption actually increases. But as we know, this is not a true reflection of the contribution that these systems have to offer. So if you look at the second figure on this slide, it's showing us the primary energy consumption with just the microgeneration systems individually implemented on the building. And as we can see, it's about 50 to 55% reduction in the primary energy consumption with just that one measure implemented on the building. Next, we're looking on the first figure, we're looking at the carbon emission reductions. And once again, the measures had varying degrees in terms of their contribution. Some of them provided very little reduction, such as the insulation measures, whilst others resulted in a more significant reduction. For example, the renewable HVAC microgeneration systems. And the next figure on the slide is showing us the energy savings against the cost savings. So generally, the energy and cost savings were the lowest for the insulation, lighting, and glazing. And for most measures, the energy and cost savings were positively correlated. So measures with higher energy savings also ended up having high cost savings. But for certain measures, for example, the biomass boiler, it had much larger energy savings than its cost savings. And then the mechanical ventilation, for example, had little energy savings in comparison to its cost savings. So the main takeaway from the previous two slides is that none of those measures were able to completely reduce any of the indicators to meet our required target. And so implementing the measures separately sort of tells us that actually to reach the NZEB standard, we need several measures to be implemented together. So the next phase of analysis involved implementing different combinations of energy efficient measures until the NZEB target is reached. So this table is showing us the, I guess, the best performing energy efficient measures out of the ones we trialed. We selected them and then we decided we're going to combine them initially as sets of 2 and then 3 and so on until all the possible different combinations have been explored, as you'll see over the next 2 slides. So looking at the first set of 3 figures, we're looking at our energy consumption, carbon emission, and primary energy consumption for a combination of 2 energy efficient measures together. And the main conclusion to be drawn from the first 3 figures is that the NZEB target, once again, is not achievable just by incorporating 2 energy efficient measures, and a combination of insulation and glazing resulted in the smallest reduction, so it was the least favorable combination. And then looking at the next set of 3 figures with 3 energy efficient measures combined together, once again, combination of 3 measures did not meet the NZEB target for the energy consumption or the primary energy consumption, and the CO2 emission target was only met when we had a HVAC, or renewable, or a microgeneration system in place as part of the retrofit package. And implementing lighting, a HVAC domestic hot water measure, and a microgeneration measure together resulted in the largest reduction for all of the indicators together. And combining insulation, glazing, and lighting was the least favorable combination. So looking now at the first set of 3 figures on this slide, we're looking at 4 energy efficient measures being implemented together, and combining those 4 energy efficient measures was sufficient to reduce the carbon dioxide emissions and the primary energy consumption target to meet the NZEB target. And for this case study for NZEBs in general, we're using the primary energy consumption as our main indicator, and the reason for this is because Annex 1 of the EPPD stated that the energy performance of a building needs to be expressed in a transparent manner, so it needs to have a very clear definition, and it needs to have a numeric indicator of primary energy use. They also stressed on the fact that whilst you can use other indicators, you can't neglect setting a specific value for the primary energy consumption. And so with these combination of 4 energy efficient measures incorporating insulation, lighting, HVAC domestic hot water, and a microgeneration system offered the biggest reduction. Looking at the next set of 3 figures, which is all of the measures combined together, actually this didn't end up offering us any additional significant savings. In fact, the savings was the difference in savings was less than 12%. And the main reason for this is because it meant we were combining insulation and glazing together, so it didn't really give us any substantial reductions, but the energy consumption does benefit the most from the incorporation of all those measures. The final case study we're going through today is Hilton Watford. It's located in Elton Way, Watford. It's a purpose-built hotel. It was constructed in the early 90s and it's spread mainly over 2 buildings. The little building that you see there on the side is just the staff accommodation. Here we have our case study summary, and the hotel is constructed of traditional bricks. It's got a flat roof, double glazed windows. The typical occupancy is 24 hours, 7 days a week. It has some cooling systems in the main areas as well. So for this case study, we wanted to do a life cycle cost analysis and select a cost optimal solution. So we decided to retrofit the packages into 4 different categories, and these were specifically designed to somewhat replicate the routes that were initially suggested by the government's new proposal for the Future Home Standard, with some variations to also reflect some of the ways the NZEB standard is achieved across the literature, and also via some commercial routes to achieving the NZEB standard. So just going through them very briefly, the first one, we're looking at significant fabric and lighting improvements, and then little improvements to the HVAC, accompanied by an undersized renewable or microgeneration system. Second one is significant HVAC improvements, and then little improvements to everything else. And then third one is an all-round retrofit, which ideally is what an NZEB should be. It should be a low energy demand building that's complemented by a renewable microgeneration system, as we've mentioned earlier. And then the fourth one is small fabric and lighting improvements, and then significant HVAC and renewable or microgeneration systems. So this table here is showing us the list of all of the individual energy efficient measures that were selected to aggregate the retrofit packages. So those individually considered measures ended up forming just under 190 NZEB retrofit packages. So as I've mentioned in the previous slide, we had 4 different categories, and then within each category we had 46 NZEB retrofit packages. They've been labelled as EP 1.1 to EP 1.46, as you will see in another figure later on. Each energy efficient measure has been defined by its own individual codes, such as IG 1.0, RM 2.1, and so on. And the selection of those energy efficient measures was defined by a parameter that's shown in the last column, and the parameters were selected so that they exceed our target by no more than 20%. For example, we have a U value of less than or equal to 0.15. It means that the wall insulation energy efficient measures will all have a U value in that range. And this variation is included because we also need a variation in the energy performance and costs and life cycle costs. That way we can have a range of different and possibly more cost-effective solutions. All of the relevant system efficiencies are also included in that column. So once again, here we're looking at our model validation for this case study. So we're comparing the actual energy consumption with the modeled energy consumption, and this time there's an 8% difference, and this 8% is an underestimation of the actual energy consumption of the hotel. And if you look at the energy profile for the actual energy consumption, which is the purple line, we can see some unusual fluctuations during certain months. And the reason for this anomalous profile is because of the year that we selected. So in 2018, the UK had very low temperatures, and we even had snow during February, March time. And then after this, we had a heat wave during April, and we had some very warm days. But when we compared the annual actual energy consumption of this year, 2018, to the actual annual energy consumption of the previous 2 years for the hotel, we found that the difference in the total was less than 5%. So it didn't really matter which year we selected, because it didn't have any effect on the results or the validation of the model. But what this tells us is that possibly the hotel's current energy consumption is affected by other factors and activities that are not necessarily weather dependent. Also possibly that the hotel's energy management could be improved upon. So here we're looking at our primary energy consumption and carbon dioxide emissions with our retrofit packages. So as I said, it's 4 different sets of categories, and within each category we have 46 packages. And then we're comparing this to our, again, baseline indicator and our NZEB target. Adopting the the methodology where we focused on, or different retrofit packages focused on different potential retrofit aspects, really just showed us, or proved to us, that a whole building retrofit is the best route to achieving the NZEB standard. When you prioritize one aspect and then you neglect another, it just leads to this incomplete retrofit that either doesn't lower your energy demand or doesn't improve and optimize the overall energy efficiency of the building systems, components, and so on. Also, another thing is that it's not just about selecting a range of energy efficient measures that tick off the standard, but selecting suitable energy efficient measures. And suitability is something that is always going to depend on the baseline building, so its current energy demand, usage, occupancy, and so on. For example, for this case study, the most compatible packages were the ones that offered a balance between the heating and cooling needs during the heating and non-heating season. So packages that only focused on meeting the heating needs underperformed at reducing the primary energy consumption. So here we're looking at our global costs and primary energy consumption, our cost optimal graph. And as we can see, there's quite a clear distinction between the packages that made up the 4 different sets. So packages within set 1 and 2 ended up having the highest global cost in comparison to the other 2 sets, whereas packages within set 2 and 3 perform similarly in terms of their cost performance. Now, unfortunately, once again, there was a 30% gap between the cost optimal solution and the NZEB target. And it might just be that, with the current level and price of technologies, especially for retrofitting, finding a balance between the energy and cost benefits is necessary. Even small changes in the type of measure selected, for example, rather than selecting 110 millimeter of a certain insulation, you can select 80 millimeter, will help in reducing the global costs and bridging that gap. Another thing is that we have to remember that buildings are dynamic and they're not static, and at certain points they're always going to need old components to be replaced. So we need to raise awareness and educate stakeholders, landlords, that these points should be seen as an opportunity for improvement rather than just a like-for-like replacement. In this way, you can have an energy efficient building that's achieved over several stages rather than at once, because one of the main barriers to reaching the NZEB standard is usually the very large investment costs. Yeah, so just some concluding remarks to finish this off. So some of the work that we've presented here was just it proposes some of the first steps and I guess cautions towards how we can effectively begin to include the concept of NZEBs within the current UK building stock. And the approach undertaken needs to be considered carefully. It's very important that we understand the risk, because if we don't, it will be down to luck whether or not these energy efficient buildings are going to continue performing to the same standard many years down the line. So, you know, buildings need to be future proofed. The cost optimal solution is something that needs to ideally represent the best combination of energy and cost performance. It's very important to strike a balance between the two. If you plan something that's just focused on lowering the cost, then you're not going to meet the NZEB target. And, you know, likewise, focusing on just meeting the NZEB target with the current level and cost of technologies, it will mean that the solution is economically unfeasible. And the reason why we're stressing so much about, you know, economic feasibility of these retrofit packages is because the EPPD stated that in cases where you conduct a life cycle cost analysis and it's the life cycle cost analysis proved to be negative rather than positive, then you don't actually need to apply the NZEB standard. Also, here we're dealing with existing buildings, which obviously presents more challenges in terms of cost, because for a new building, the payback of the incorporated measure is usually the difference in cost between the standard available option and the energy efficient one. But for when you're retrofitting something, a component or envelope or equipment that are still functional, it means that this new measure will need to produce a payback for the cost of the entire alternative measure, and not only the cost difference between standard and alternative, which is why you have a lot of studies saying that it's not that much more expensive to build an energy efficient building from scratch. But when it comes to retrofitting, it's a bit different. But yeah, just overall, I mean, the technology is there to deliver energy efficient homes. You know, regulations around ventilation and overheating and all of that need to keep up with those improvements in the energy efficiency of buildings as well. And we do need a more coordinated approach to the requirements for energy and ventilation in buildings. Yeah, that's all. Thank you very much for listening.
Thank you very much, Radova and Ali. We got a lot of questions. What I try to do in the background is group them into the most popular ones. So I will try to summarize. One of the most popular questions is whether the projections in your work have taken into consideration future emerging technologies.
If I may, we have considered, as we mentioned during the presentation, combined heat and power and combined cooling and heat and power. We look at some of the existing technology like biomass and photovoltaic panels, but of course there is always room for improvement, because the new technologies keep coming and then it has to be considered. So what we presented here is the study we have done from 2018 till now.
One of the technologies that was mentioned quite a lot is the heat pumps. As you know, it has heavily featured in various policy documents in how to achieve net zero carbon. And the question that kept coming up is why we haven't considered heat pumps in the domestic, especially, and also the reverse cycle for cooling in the retirement village.
This was mainly the property we have considered, and the case study we considered was the existing building. And we had a collaborative study, for instance, with Hilton or with the retirement village or the homeowner. The heat pump, they were in the favorite choice because the cost associated with it and amount of the land is required. So we have to adopt something that, as we mentioned many times in the presentation, that the investor is happy to go ahead with it among the choices they have. Then it seems currently, at least, the heat pump for an existing building, it makes people terrified when they think about the construction and the cost is coming with it. But for new building, it might be a good choice because they can have it in place when they are planning it rather than then enforcing it after the building it is constructed.
Also, can I add that right now we're trying to decarbonize the power sector and obviously reduce its carbon intensity, and you know, the sectoral decarbonisation approach scenario to meet the limiting of global temperature rise to 2 degrees Celsius. If this is accomplished, then it's expected that there's going to be a 40% decarbonisation of the grid by 2050. And also recently, BEIS published a report saying that, you know, the grid carbon factor is predicted to decrease from 212 grams, I think, to 50 or 66 grams between 2017 and 2035. So, you know, in that case, CCHP units might eventually no longer make an effective contribution to reducing emissions, unless, of course, you start running them in times of higher carbon intensity. So, you know, or if you start coupling them with like thermal storage so that they could export electricity or reduce demands during periods of high demand on the grid. So yeah, and like I said, Dr. Ali mentioned this as well, with CHP and CCHP, you do end up exacerbating the risk of heat island effect. In which case you need to think of alternative systems. So for CCHP, one alternative system is the absorption chiller based would be the aquifer thermal energy storage system. And in this case, you've got excess heat pumped into aquifers during the non-heating season, and then it's extracted once again for heating during the winter. And this actually has been applied within a housing scheme in, I think, southwest London and also in the Netherlands. So there are alternatives, but with the current available technology, it's not going to be widely recommended.
Thanks, Radwa. That's very useful. Another question that is relevant that came up a couple of times is what type of fuel was considered when modeling the impact of CHP and CCHP now and in the future? Gas or biofuel?
Natural gas.
Okay, thanks.
Yeah.
The other popular question is about the carbon conversion factors. A couple of people on attending the webinar, they said that they are out of date, they're too high. And
yes, and like Dr. Ali mentioned, yeah, so this study, I conducted it when I first started my PhD, like in 2017. So this is why they're obviously not up to date.
So do you think it's worth looking at the results by using the latest conversion factors, and perhaps, and perhaps look as well how they might change in the future if we can find get access to some projections?
Yeah, that would be very interesting to investigate, definitely.
So perhaps for the next 6 months we can update the results. Based on that. Great. There is a really interesting question that I would like to bring up as well, but it came up on the list, is how the NZEB and the net zero carbon strategies align, and should they align, or are they aligned at the moment? Should they align? If not, and how do you see the kind of the two strategies going in the future?
For me personally, I think they should align. At the moment with nearly zero energy buildings, it's still a bit up in the air, so we still don't have any concrete definition or methodology. So to comment on whether it's aligned or not officially, that I don't think we'll be able to say that, whether it is or not.
Mm-hmm. Do you think the net zero carbon strategy is more clear?
To an extent, yeah. I mean, we have, I know that CIBSE have the ILETI, so net zero operational carbon, which is very, very similar to what we've been talking about here. And I feel, you know, the two concepts should align, but it will be up to like what sort of legislations come up, whether they do align or not.
Okay. Let's see.
And probably we can
Yes,
just add, there is another regulation, probably everybody heard about it, as a minimum energy efficiency standards for MEES.
Yes.
Perhaps that could be another line of the research to see how the minimum or MEES or minimum energy efficiency standard and how NZEB they align together and where they stand, because the other one is a little bit more clear and they provide more detailed specification. But this is the area we are thinking about it, because we have another research is currently carrying on this minimum energy requirement. So the next stage is to see, compare these two regulations and see where they stand, each of them. But we are hoping to provide the result of that within maybe the next few months.
That's an excellent idea, Ali. I think perhaps we need to sit down and think about doing this comparison, and then perhaps we can put it online for people to download. That would be really useful to show that the study that Radwa has done is actually relevant to the net zero carbon agenda and the MEES agenda as well. I will just ask a final question because we're running out of time. Which is, what are your recommendations for most cost-effective measures for residential homes? And I would think that that aligns with the latest announcement regarding the retrofit bill and that the government just announced yesterday. Ali, if you want to go first. Or Radwa.
As we mentioned, the property to property will be different, depend on the age of the property, but my personal view, currently the most cost-effective one will be the photovoltaic panel, because you are not going to endanger the overheating. We mentioned briefly that most of the current measure is going to cause the overheating of the building, but implementing the micro generation like a photovoltaic panel is cost-effective and is not going to cause the overheating of the property.
Yeah, it also depends on, sorry?
That might be a bit outside of people's price range. That would be my first kind of response to that. Yeah, sorry, Radwa, go on.
Yeah, so what I was going to say is that it really depends on whether you're dealing with a house or an apartment as well, because if you're looking at a house, for example, I would say focusing on the air tightness of the house, including insulation, improving the insulation, especially right now for the UK, and for houses, because you do have a lot of ventilation and you can incorporate shading like, you know, blinds or curtains, then that would be one of the best ways to start, by reducing the energy demand of the building initially. Other small things would be upgrading the building, the HVAC systems. But again, like in terms of cost efficiency, it really will depend on the stakeholder or the landlord.
Okay, well, I think I'm going to close the webinar here. Thank you very much to Radwa and Ali for the presentation, and thank you all very much for attending. As I said before, you will receive an email tomorrow with a link to the webinar slides and the audio, and also there's going to be a link to the Research Inside, which is the publication that includes the results from this study. Thank you all very much and have a good day.
Thank you.
Thank you.